This is the screencast for section 2.6, example 6. All right, so we're going to do some more analysis of rational functions. I know, you love doing this. I'm going to try and make this as clean as possible for you in terms of I'm not going to show you a lot of my work because we have been doing this for so long. But if you do have any questions on the basic concepts, please go back to section 1.2. That's where you initially learned all of the characteristics of a graph. So here we go. I'm going to factor the original function. That factorization can give me a lot of information. My domain, let's see, positive 2 and negative 2 need to be left out of the domain. Because positive 2 and negative 2 only make the denominator 0, that means they are going to be both infinite discontinuities as well as vertical asymptotes. Speaking of asymptotes, the degree in the numerator is the same as the degree in the denominator. So if I look at the leading coefficients, I get 2 divided by 1, which then means y equals 2 is the horizontal asymptote. If I plug in negative x to the f function, I can find the function's symmetry. After plugging in negative x, I see that I end up with the exact same thing I started with, so the symmetry of this function is even. I can also algebraically calculate the intercepts, x and y intercepts, by plugging in 0 for y and x, respectively. I found that positive 1 and negative 1 make the function equal to 0, so those 1 comma 0 and negative 1 comma 0 are my x-intercepts. My y-intercept I found after plugging in 0 for x was 0 comma 1/2. Now I'm going to sketch a coordinate plane with all the information that I found so that my sketch of the function can be as accurate as possible. Now in my calculator, I have graphed the function as well as found the maximum, because that was I did see that there was a maximum there. That's like the piece of information that's missing that I can't find without my calculator. The maximum is actually the y-intercept, which makes sense. This is an even function. So the function will be increasing until the y-axis, but then it has to repeat that same thing on the other side, just the opposite. So it's going to decrease after that. So the spot on the y-axis is where the function will change from increasing to decreasing. So there is a local maximum at 0, 0.5. So now because I have the local maximum, I can make my accurate sketch of the graph, including any maximum that might occur, or any extrema in general that might occur. So the left piece of the graph approaches the horizontal asymptote and the vertical asymptote. The middle piece of the graph will go up to the maximum and come back down, approaching both asymptotes. And then the right piece of the graph also approaches both asymptotes up in this upper right-hand corner here. This will help us determine the range. The range is going to be, so the y values used are negative infinity up till this maximum y value, which was 1/2, and we are going to include 1/2. Then, just after the horizontal asymptote of 2, all the way up to infinity, we're using those y values as well. But there is this vertical gap between y equals 1/2 and y equals 2 that is not being used. Now, because my range does go from negative infinity up to positive infinity, the boundedness is unbounded. This function does change from increasing to decreasing, so we have to put some thought into the increasing and decreasing portion. We're increasing all the way up to the maximum, leaving out the vertical asymptote. Then we're decreasing after the maximum, again leaving out the vertical asymptote. The parts of the function that are above the x-axis, so the y values that are greater than 0, occur all the way from negative infinity up until the vertical asymptote. But then a portion of the graph drops below the x-axis. So from the vertical asymptote until the x-intercept, we're below. So the y values are negative. Then we go back above the x-axis from negative 1 to positive 1 for this little piece right here. Then we dip below the x-axis, so from positive 1 to positive 2, the vertical asymptote. We are below the x-axis. Then we go back above the x-axis for the remainder of the graph, so after the vertical asymptote all the way out to infinity. There are again 6 end behaviors to describe. The 2 end behaviors associated with the horizontal asymptote, both as x approaches positive infinity and negative infinity, both, the y values, or f of x values approach 2, the horizontal asymptote's value. The end behaviors associated with the vertical asymptote both have x approaching -2, but from the left and from the right. As we approach -2 from the left, the y values go up to positive infinity. As we approach the x value -2, the y values go down to negative infinity. And the last two end behaviors are associated with this vertical asymptote. The limit, as x approaches +2 from the right, the y values go up to positive infinity. But as we approach the x value +2 from the left, the y values go down to negative infinity. The now try problem for example 6 is number 41. Here we go, more analysis. So +3 and -3 have to be left out of the domain. Both positive and -3 only make the denominator 0, so they are both infinite discontinuities and vertical asymptotes. Degree in the numerator is the same as the degree in the denominator, so the horizontal asymptote will be the leading coefficient divided by leading coefficient, which in this case is y equals 1. I'm going to plug in -x to test for symmetry. After plugging in -x, I do not have the exact same thing I started with, nor do I have the exact opposite, so there is neither symmetry, neither odd nor even. I'm going to find the x and y intercepts. When I plugged in 0 for y, I got the x values 1 and -2 that would make the function equal to 0, so the x-intercepts are 1, 0 and -2, 0. When I plugged in 0 for x, I got 2/9 as the y value that came out, so the y-intercept is 0, 2/9. Now I'm going to set up my x and y coordinates so that I can have an accurate sketch. Now I graphed the function on my calculator and also found the maximum because I could see kind of with my preliminary information here that the graph was going to change from increasing to decreasing. So I found the maximum, which is at -0.68, 0.26. It's a local max. So now I plotted that maximum, which also gives my function a better path for my sketch because I can see that it comes up through the x-axis, hits the maximum, then comes down through the y-intercept and down through the other x-intercept. So I can create the sketch of my graph according to the pieces that my calculator showed me. Range of this function is going to go from -infinity up till that highest y value, which the maximum y value was 0.26. Then after the y-intercept, after the horizontal asymptote, all the way up to infinity. The function increases up till the x value of the maximum and then decreases after that, leaving out both vertical asymptotes. Since the range of the function goes all the way down to -infinity and all the way up to positive infinity, it is unbounded. So from left to right, the function is above the x-axis all the way out from -infinity up till the vertical asymptote at -3. Then the function drops below the x-axis from the vertical asymptote at -3 till the x-intercept at -2. Then the function is above the x-axis, above the x-axis from the x-intercept to x-intercept, so from -2 to +1. Now from +1 to the vertical asymptote, the function is below the x-axis, so from 1 to +3. Then after the vertical asymptote, the function is above the x-axis forever, so from +3 to infinity. There are again 6 end behaviors to describe. The end behaviors associated with the horizontal asymptote, the y values both approach the horizontal asymptote value of 1 as x approaches -infinity and positive infinity. And behaviors as the function approaches the vertical asymptote from the left and the right at x equals -3 are positive infinity and negative infinity respectively. The end behaviors as the function approaches the vertical asymptote at +3 from the left and from the right are negative infinity and positive infinity respectively.